In the last video, we talked about quantization, making models smaller so they fit on consumer hardware. If you've watched that, you know a 70 billion parameter model at 16-bit takes 140 gigs, but at Q4_K_M it's more like 40. That's how local AI even became possible. But there's a problem that quantization doesn't solve. Even after you squeeze the model into your GPU memory, it still generates text one word at a time. Slowly. Painfully slowly. 15, maybe 20 tokens per second on a good day. You watch the cursor blink. You wait. Now, what if I told you that you could get 2 to 3 times faster generation, same model, same output, mathematically identical, and the trick involves generating more tokens, not fewer? That's speculative decoding. And it's probably the most counterintuitive free lunch in AI inference right now. To understand why speculative decoding works, we have to talk about what's actually slowing your LLM down. And the answer might surprise you. Your GPU is not compute bound. It is memory bandwidth bound. Here's the deal. A 7 billion parameter model stores about 14 gigabytes of weights in VRAM. Every time that model generates a single token, every single one of those 14 gigs has to travel from VRAM across the memory bus into the compute units. That's a lot of data movement. An RTX 4090 has about a terabyte per second of memory bandwidth. So the absolute fastest you can do one forward pass is 14 gigabytes divided by 1 terabyte per second, about 14 milliseconds. That's a hard floor. You cannot go faster than the data travels. And here's the kicker, during that pass, the math itself, the matrix multiplies, the attention mechanisms, takes a tiny fraction of that time. The compute cores are mostly idle, waiting for the next chunk of weights to arrive. Prompt processing is different, by the way. When you feed in your entire prompt at once, the GPU can batch it and saturate the compute units. That's fast. But token generation? One token at a time? The compute units are bored. So the bottleneck is clear. Every single token requires reading all 14 gigs of weights from VRAM. The compute units are basically free once the data arrives. But what if we could get more work out of each read? That's the idea behind speculative decoding. We introduce a second, much smaller model, the draft model. This could be a 1 billion parameter model, maybe 100 million, tiny compared to the 7 or 70 billion parameter target model we actually care about. The draft model generates a few tokens the normal way. One by one. But because it's small, say 2 gigs of weights instead of 14, it moves through memory much faster. It proposes, say, 5 candidate tokens in rapid succession. Then comes the trick. We take all 5 proposed tokens and feed them into the big model in a single forward pass. Not 5 separate passes, one pass, processing all 5 positions at once in parallel. Here's the part that breaks your brain, that single parallel verification pass takes almost exactly the same amount of time as generating a single token. Because the bottleneck is reading those 14 gigs of weights from memory, and we already read them. The extra compute from handling 5 token positions instead of 1 is negligible. The cores were bored anyway. So the draft proposes 5 tokens in 2 milliseconds each, 10 milliseconds total. The target verifies all 5 in one pass, 14 milliseconds. That's 24 milliseconds of work to potentially get 5 good tokens. Compare that to the normal way, 5 tokens, 14 milliseconds each, 70 milliseconds total. Let me hammer this point home, because it's the entire foundation of why speculative decoding works. The cost of a forward pass through a transformer is dominated by reading the weights from memory. The actual math on those weights scales with how many tokens you're processing, but on a consumer GPU with batch size 1, the memory bandwidth is the bottleneck by a wide margin. So when we process 5 tokens in the verification pass instead of 1, we read the same 14 gigs of weights. The compute time goes up a little, maybe 20% for 5 tokens. But the memory time is exactly the same. This is the seesaw moment. On one side, generate 1 token normally, read all weights once, 14 milliseconds. On the other side, verify 5 tokens speculatively, read all weights once, 14 milliseconds plus a tiny compute bump. You are getting up to 5 times the output per memory read. That's where the 2-3x overall speedup comes from. It's not magic. It's exploiting the physics of how GPU memory works. Now, you might be thinking, okay, but the draft model makes mistakes. It proposes tokens the big model wouldn't have chosen. Don't those mistakes change the output? This is the most beautiful part of speculative decoding. It doesn't matter. The verification step doesn't just blindly accept the draft tokens. It uses something called rejection sampling, a Metropolis Hastings scheme from statistics that's been around for decades. For each proposed token, the target model compares its own probability distribution to the draft models. If the draft proposed something the target agrees with, great, accept it. If the draft proposed something unlikely, the target rejects it and resamples from a corrected distribution. The acceptance probability is the ratio of the target model's probability to the draft model's probability. And if the draft was actually more confident than the target? You just accept. The math guarantees that the final output distribution is exactly what you'd get from running the target model alone. Zero approximation. Zero degradation. It is mathematically identical. This is not a heuristic. This is not a lossy hack. This is lossless acceleration, and that is extremely rare in machine learning. Let's talk about what this looks like in practice. On an RTX 4090 running Llama 3.18b at Q4_K_M, you'll get about 55 tokens per second normally. With speculative decoding using a Llama 3.21b draft model, that jumps to 110 to 130 tokens per second. Roughly 2 to 2.3 times faster. On an RTX 3090 with Llama 370B at Q3_K_M, that's an enormous model squeezing into 24 gigs, you go from about 8 tokens per second to 16 to 18. 2 times. On a Mac with Apple Silicon, running Mixtral 8X7B at Q4 with a tiny 360 million parameter draft model, you go from 30 tokens per second to about 55. Nearly 2 times. The numbers vary by task. Code generation sees the biggest gains, sometimes over 3 times. Creative writing gets less, maybe 1.2 to 1.5. But the average across most workloads is consistently around 2 times. And here's how you actually try this. If you're using llama.cpp, it's a few flags. Draft max 5 draftman 3 draft model your _draft model.guf. You need the draft model to share the same tokenizer as your target model. That's the main constraint. Models from the same family, like Llama 3.21b with Llama 3.18b, work perfectly because they share the same vocabulary. Also, quantize your draft model too. A Q4_K_M draft takes almost no VRAM, and since both models need to fit on your GPU simultaneously, keeping the draft small matters. The draft model approach is the simplest form of speculative decoding, but researchers have developed some clever variations. Medusa, from Together AI and CMU, eliminates the separate draft model entirely. Instead, it adds multiple small prediction heads on top of the same base model. Each head predicts the next token, one head predicts token at position +1, another predicts +2, and so on. Since they all share the same base model hidden states in a single forward pass, you don't need to load a second model at all. Trade-off: you need to train those heads first. Eagle, from Peking University, goes a step further. Instead of predicting tokens at the output level, it predicts the hidden states inside the model itself, the features. This gives the draft much richer information about what the target model would actually generate. The result is higher acceptance rates, and Eagle 3 claims up to 4 times speedup on some benchmarks. Then there's self-speculation, using the same model as both draft and target, but at different quality levels. Maybe a heavily quantized version generates the draft and the full precision version verifies. Or you exit early from a few layers to generate the draft. No extra model download, no extra storage. These are all active research areas, and they're getting integrated into tools like llama.cpp, VLLM, and TensorRT-LLM as we speak. Speculative decoding is powerful, but it's not a silver bullet. Let me be honest about the limitations. First, VRAM. You need room for two models. A draft model adds 15 to 30% more memory usage. If you're already right at the edge, say, squeezing a 70 billion parameter model into 24 gigs, you might not have space for a draft. Quantizing the draft helps, but it's still a constraint. Second, speedup varies by task. Code completion and summarization, predictable, structured text, can see 2 to 3 times speedup. Creative writing, poetry, open-ended brainstorming? You might only see 1.2 to 1.5 times. The draft model is guessing, and creative text is harder to guess. Third, this primarily helps at batch size equal to 1, the local inference case we all care about. If you're serving hundreds of users simultaneously with large batches, the verification pass becomes compute-bound and the advantage diminishes. And fourth, your draft and target models must share the same tokenizer. If they use different vocabularies, the draft token 42 means something completely different in the target model. This limits which models you can pair. Speculative decoding is moving fast, and the next generation of approaches look even more ambitious. Meta is researching multi-token prediction training models from the start to anticipate multiple future tokens. If models are born seeing ahead, speculative decoding becomes a natural inference strategy instead of a post-hoc optimization. Google DeepMind's Looking Glass, from 2025, proposes speculative decoding without any draft model at all. Instead, the target model uses a look-ahead mechanism to predict its own future hidden states, 2 times speedup with 0 extra storage. And future hardware may include dedicated draft accelerators on the GPU die itself, tiny coprocessors whose only job is to run fast draft predictions while the main compute units handle verification. We're moving toward a world where inference at the edge feels as fast as the cloud. Quantization and speculative decoding are the two pillars that make that possible. Quantization shrinks the model. Speculation makes the generation faster. Together, they compound. Speculative decoding is available right now in Llama.cpp, VLLM, and TensorRT-LLM. If you're running local models, try the draft model flag, you might double your speed with 0 quality loss. If this video helped, subscribe for more deep dives into what makes local AI actually run. And drop a comment, what's your current tokens per second? I'd love to know what hardware and models you're running. Thanks for watching, and I'll see you in the next one.